Okay, Alhamdulillah, finally. So this is the last topic in chapter 4. Okay, so the line coding is different from the PCM coding. You remember we have our PCM, okay, which is okay, it has three main processes: sampling, quantization, and coding. So the coding here is different from the line encoding. So the line here refers to the transmission line, or the physical medium. So it's very related to the channel or medium, because this one output is bit 010, the bit series, but it needs to be represented. Our 1 and 0 can be represented using many formats. So this format is known as the line coding. And the line coding format, it affects many aspects of our transmission. And then there are several considerations when we choose our line coding formats, because it has differences in terms of the transmitted voltage, the duty cycle, the produced bandwidth, and also the abilities to perform processes like synchronization, error detection, error correction, and so on. Okay, so let's look at the next slide. Okay, how different format can produce has different transmission voltage or power efficiency. Okay, so the way that we represent our signal, okay, because 1 and 0, we can give either different values, different or different voltages. Okay, for example, if we want difference of 5 volts between 1 and 0, it can be represented using voltage 5 and 0. 0 for bit 0, 5 for bit 1. Or we can use minus 2.5 volt for bit 0 and plus 2.5 volt for bit 1. Okay, so let's look how it leads to different power efficiency. Let's say consider bit 1 and bit 0. So this is presented by the voltage 5 volt. This is 0 volt. Okay, so what's the average power to transmit these two bits? Okay, to transmit bit 1, it's V, assuming R equal to 1 ohm, so it's just V squared, so 25 watt. And this one, 0 watt. So what's the average? So it's 25 plus 0 divided by 2, which is 12.5. If we use 2.5 and minus 2.5, what we got is, and so this is the voltage, the power is 2.5 square and minus 2.5 square. So in here we got the power equal to 2.5 square, 6.25. This is also 6.25. So the P average to transmit these two bits is 6.25 plus 6.25 divided by 2, 6.25. So you can see the difference. This one uses more power. Then, so this is known as unipolar, because it has only one polarity, the positive. And this is bipolar, where we use both positive and negative polarities to represent our bit 1 and 0 respectively. Okay, so using unipolar and bipolar can lead to different power efficiency performances. Okay, so this is for the first part. For the duty cycle, what is duty cycle? Okay, if we have our bit 1, for example, and this is the whole bit duration. Okay, this is the whole bit duration TB. So duty cycle is the ratio between the active bit period of active bit time over bit period. So active bit time, for example, if our active period is only half of the TB, like this, yeah. So 1 is represented by this, where it's active only half of the TB. So this is known as top. Yeah. So duty cycle is equal to over TB. Okay, if this one is just 1.5 TB, then our duty cycle is 0.5 or 50%. Okay, so this is also known as the return to zero. And there's another form which is non-return to zero. NRZ is non-return to zero. For NRZ, the thought is equal to 1. So its active bit time is similar to bit period. Okay, bandwidth requirements. So the bandwidth that is required to transmit certain line formats differ depending on the transition of bit sequence. Okay, I'll show this. What does it mean? And synchronization is when, because in digital communication, we have to differentiate bits that belong to a certain period. So what's the current bit, next bit, and so on. So if we have long strings of 0 and 1, there can be problem of synchronization when we have delay. So basically we need, how are we going to be able to differentiate or distinguish certain bits? So bipolar RZ has good synchronization performance, because for RZ actually, compared to NRZ like this. Okay, 1, 1, 1. So it's like this, NRZ. For RZ, like bipolar, okay, 1 is another 1, this. So we know that, okay, even though it's a consecutive bit 1, 2 bit 1s, this one will return to 0. Okay, we know that when we have this return to 0, next will be belongs to the another bit. So we should be able to distinguish better compared to the like NRZ. So and error detection and correction, because certain formats or codes has mechanism for error detection and coding, meaning that when you're given a certain sequence, you can identify or you can notice that there's an error in that sequence. So format like RZ AMI has built-in error detection mechanism. Here AMI refers to alternate mark inversion. Alternate mark inversion. So in communication, 1 and 0 is also known as mark and space. Okay, bit 1 called mark, bit 0 space. Okay, so they are another names for them. Okay, let's move to the next slide. Okay, so this slide basically we want to demonstrate how you get this bandwidth that's required to transmit certain formats. Okay, so the highest fundamental frequency is determined by the fastest transition in the bit sequence. Let's say for this bit sequence, the fastest transition is from here, and we have also transition from here, but this sequence has much faster transition. So, okay, so this T here takes 2 TB, okay? 2 time taken for this fastest transition is 2 TB. So F then is equal to highest fundamental frequency, then is equal to 1 over T, which is equal to 1 over 2 TB, which is equal to 1 over TB is equal to FB. So it's FB over 2. Okay. So is equal to FB over 2. So that's how, if you notice in the questions that we discussed before, for the minimum bandwidth requirement is FB over 2, because that's the minimum bandwidth. For bipolar NRZ, also FB over 2. For unipolar NRZ, the fastest cycle here takes only TB. So that's why, since F equal to TB, then F time for the fastest transition equal to TB. So F equal to FB, or bandwidth equal to FB. Yeah. Okay, for bipolar RZ, it's FB. Bipolar RZ AMI takes 2 TB. Okay, so it's FB over 2. So if you notice, NRZ, even though it doesn't have much capability in terms of synchronization, error detection, etc., it's actually NRZ is the most conventional. This one, but bandwidth is less than formats such as RZ, which has better synchronization. Okay, let's move to the next slide. Okay, so overall, even to compare these 5 formats, unipolar NRZ, bipolar NRZ, unipolar RZ, bipolar RZ, and bipolar RZ AMI. So in terms of bandwidth, the average DC, clock recovery, and error detection, the most conventional unipolar NRZ has the average quite bad performance because even though it uses less bandwidth, but in terms of power, synchronization, error detection is not that good. Okay, so RZ has good synchronization, problems in terms of uses more bandwidth. Okay, in overall, bipolar RZ-AMI has the best overall quality. Okay, synchronization is less than bipolar RZ, but it's still better than NRZ. Bandwidth similar to NRZ, and it also has error detection capability. Okay, so I'll show in next subsequent slides how in RZ-AMI we can have this error detection capability. Okay. Okay, we start with first category. So in this remaining 3 slides, I'll show you some variants under certain category. Okay, category first is NRZ, none return to 0. For none return to 0, all the bits, it does not return to 0. So the duty cycle is equal, the same as the bit period or the active bit time. So it's none return to 0. There are 3 types, none return to 0. NRZL, NRZM, and NRZS. Okay, for NRZL, this is the most popular method. Okay, so basically bit 1, just 1, 1, bit 0, 0, 1, 0. Okay. But the data does not return to 0 in one clock interval. There's no synchronization, but normally you can use start bit if you want to distinguish certain fields within the frame. Okay. NRZ M, NRZ mark. We have if this is mark. If we have bit 1, there's a transition at the starting interval, and 0, no transition. Meaning that, okay, let's say we start with low. If you see bit 1, it transits at the start of interval. Right? From here to here. And then bit 0, no transition. Another bit 1, transition. Bit 0, no transition, and so on. Okay, NRZ space, it's the opposite to NRZM. 1, no transition. 0, there's transition. And then 1, no transition, 0 transition. Okay, second category is RZ. So there are a number of variants for RZ. RZ unipolar, bipolar, RZ AMI. So basically, the one that we study here is the 50% lah, where it written at the half of bit interval. Okay, so unipolar, one high level, okay, high, but it return to 0. In the middle, return to 0. Next, bit 1, bit, and then return to 0. Bit 0, low level, so just low. Bit 1, again, 1, and then return to 0. Bipolar, from 1 from positive to 0. And for negative, for 0 is negative voltage, and then return to 0. So 1, 1, 0, negative to 0, positive to 0, 0, negative to 0. RZMI, this is where it has the capability of error detection. Okay, for 0 is 0, low level, it's just low, low, low. For 1, the symbol will alternatively change. So alternately change from, say this one, bit 1, from high to 0, positive to 0. If it is another bit 1, then it will be from invert sign from negative to 0. Bit 0, 0, and then another bit 1 change from positive to 0. Bit 0, 0, 1, negative to 0. So if you notice, okay, for this bit 1 is positive, next bit 1 is negative, next bit 1 positive. So that's why it's called alternate mark inversion. The sign of bit 1 or this mark will be changed alternately. So at the receiver, if you receive a sequence of like this, you know that there's an error because bit 1 shouldn't have a consecutive bit 1 shouldn't have similar representation. So that's how RZAMI detects error. Okay, so the last category is biphase. So biphase, okay, there are also 3 types: biphase M, L, and S. So biphase M, we have this transition at the middle of interval for bit 1. So this mark, transition at the middle of interval, 0, no transition. And at every new bit, it will start opposite level to the previous bit. So that's how it have this self-synchronization. Okay, biphase L, or known as Manchester coding. If 1, it translates high to low at the middle of interval, 0, low to high. Biphase S is the inverse to biphase M. 1, no transition in the middle of interval, 0, transition in the middle of interval, and okay, at every new bit, it will change opposite S sign. So biphase L here, okay, biphase M, and transition at the middle interval for every bit 1. So here, at the middle, it transits. And then at new bit, it goes to opposite. Okay, it transit, new bit, it goes to opposite, and again it transit. And then when it is bit 0, new bit, go to opposite. And since it's bit 0, there's no transition at the middle, bit 1, and then new bit, go to opposite. Since it's bit 1, and it transit in the middle, so and so on. For biphase L, so if 1, high to low, high to low, then for 0, low to high, and then high to low is just like that. Biphase S is opposite to biphase M. Okay, 1, no transition, but since it's new bit, go to opposite. Okay, and then new bit, opposite, bit 1, transits at the middle. Okay, so sorry, bit 0, no transition. I cannot see because I have this note in the notation at top. Okay, So bit 1, no transition. Bit 0, it transits from low to high. And then bit 1, new bit, opposite. Bit 1, no transition. So those are the descriptions of the variants under each category. Okay, so normally line coding, they're not popular. It's not a popular question in the assessments. Okay, but sometimes it does come out. Okay, so normally you're asked to to sketch the digital waveforms of in different formats given certain bit sequence, and then find the minimum bandwidth. Okay, so for example, this one we are given 4 formats. Okay, and then sketch using the bit sequence is 110, 10010, so you can try yourself. I'm not going to solve. Okay, and then find the minimum bandwidth requirement. We know the NRZ. Okay, so first we need to find the FB lah. What's the bit rate, which is NFS. N is already given, 8 bits. FS, okay, it says here sampling rate twice the Nyquist frequency. So Fs is equal to 2Fn, and our Fn is 2Fm. So Fs is then 4Fm. Maximum frequency 4 kilohertz. So 4 times 4 is 16 kilohertz. And then N is equal to 8. So we got the value of our FB, 16 times 8. 1 to 8. 1 to 8 kilobit per second. So for NRZ, the bandwidth is equal to FB over 2. RZ, bandwidth is equal to FB. RZAMI, bandwidth is equal to FB over 2. 5SM, bandwidth is equal to FB. Okay. So should be able to get the answers for this. Okay, so I guess that's it for exercise on this line coding and for the format. I'll give a tutorial in your Google Classroom on PCM. And then I hope you can finish all the lessons for this chapter. Yeah, and then try to understand. Okay, don't forget to answer the review questions and also the reflection inside the e-learning. Okay, since we will have quiz, we have finished our PCM chapter as normally. We'll have quiz at the end of our chapter before we move to the next new chapter. Okay, so that's it. So just all the best for your quiz. Hope you can prepare well. If any question, you can ask in the Telegram or in the in your answer to the essay questions. So see you next week, inshallah. Assalamualaikum and very good afternoon.